Welcome to my YouTube channel. Our topic for today is functions of bounded variation and their properties. Let's begin with some basic definitions. Bounded variation. Let f be a function be given and consider a partition P defined from A to B. We say that f has bounded variation on AB if BV AB of f is the supremum of the sum of the absolute value of f of xj minus f of xj minus 1 and is finite and exists. Let's look at some important theorems with example that will help us in this course. Theorem: if f is continuous on AB and f has derivative and is bounded on the interval, then f is of bounded variation. Proof: letting the absolute value of the derivative be k for all x in AB, let the partitioning be defined from A to B. We want to prove that the bounded variation, which is the supremum of the summation, exists. Recall that f of x is differentiable on AB, open interval AB, if there exists at least a c in AB such that the derivative or the mean value theorem is defined this way, which is f of b minus f of a all over b minus a, and f of b minus f of a is equal to b minus a f prime c. Now, the bounded variation over f, which is the supremum of the summation of f of s, will now be equal to the supremum of the summation of the absolute value of f prime and the absolute value of xj minus 1. Now, f prime will now be k, you bring it out, and you have a k supremum of the summation of xj minus sj minus 1 for all sj. We have to move away from absolute value into bracket because it's a monotone sequence. So we assume that x minus sj minus sj minus 1 is going to be positive. And when you continue with the expansion, then you're going to have every other thing will cancel out and kn minus x naught will remain. So the final value will now be k in bracket b minus a, which is finite. Let's pick some examples to show that when a function is continuous, differentiable, and bounded, then it's of bounded variation. Show that the sequence of function f is of bounded variation on 0, 1, and f of x, the sequence of function is equal to x sine 1 over x and 0 when x is 0, but x sine 1 over x when x is not 0. Solution: to show that f of x is continuous at x equal to 0, we need to verify that the limit of f of x at 0 is 0. For x not equal to 0, the f of x, which is this x sine 1 over x, we take the absolute value of sine y, where 1 of over x can be called y. Discover that it's bounded at 1. So when you now take the absolute value of x sine 1 over x to the bounded at x. Now, given epsilon, we choose our delta to be equal to epsilon. Then if the absolute value of x is less than delta, we have that absolute value of f of x will be less than absolute value of x, which will be strictly less than delta equals to epsilon. Thus, the limit as x goes to 0 of f of x is 0. So f of x is continuous on the interval 0, 1. Next, we'll check for the derivative. We'll find the derivative of f of x, and it will give us x squared cos 1 over x in bracket minus 1 over x squared plus 2x sine 1 over x. And the absolute value of that will give us 1 plus 2 times 1 times 1, which will give us 3. So the bound of that function is 3. We have seen it is continuous, we have seen it is differentiable, and we have seen the bound also to be 3. So our conclusion will be that that sequence of function f of x is of bounded variation. That's what the theorem says. Another important theorem in this topic is if f is monotonic on AB, then f is of bounded variation on AB. So let f be monotonically increasing on AB, then the bounded variation will be the supremum over P, which is the partition of summation of f of j x j minus f of a j minus 1. When you do a proper simplification out, some of them will cancel out each other, and we have f of xn minus f of x naught remaining. So f of xn, we call it our f of b, while f of x naught, we call it our f of a, which is also finite. Let's show with an example what we mean by monotonically increasing function. Now, show that f of x is a bounded variation on the interval. Solution: the derivative is 2x plus 1. Hence, this derivative is 0, implies that 2x plus 1 is 0 and x is greater than or equal to minus 1 over 2. Therefore, f of x is monotone increasing on minus 1, close interval minus 1 over 2 and 1. Similarly, if the derivative is less than 0, it implies that 2x plus 1 will be less than or equal to 0, and x will be less than or equal to minus 1 over 2. Therefore, f of x is monotone decreasing on minus 1, 1 minus 1 over 2. Then f of x is a bounded variation. What we just did here is to prove that the function is monotone increasing. You see, there are so many other ways we can use to prove it, either by using the ratio test, by using calculus, or by using other means to do it. Now let's look at another important proof here. It's a proof that a function of bounded variation is bounded. Proof: let f be a bounded variation, then this definition for bounded variation will hold. Okay. Now let bv of f be less than k. We want to prove that the absolute value of f of x will be less than or equal to t for all x in a interval, close interval ab. Now our f of x is equal to f of x minus f of a plus f of a. That is, we added a special 0 to f of x so that we can make some expansion there. And when we have done that, we are going to have the bounded variation plus f of a. And that bounded variation is k, while f of a remains, and the summation is equal to t. Let's look at one example which shows that a function can be continuous but not in a bounded variation. However, for a function that is continuous to be of bounded variation, 3 properties must be satisfied. Number 1, it's continuity, it must be differentiable, and it must be bounded. But in this particular case, this one is continuous, it is differentiable, but it's not bounded. So firstly, we prove that f is continuous. We need to verify that the limit from the left and right side, that is the directional limits, are equal to 0, and the f of x is equal to x cos pi over 2x. Since cos s is bounded by 1 for all y, it follows that the absolute value of x cos pi over 2x is less than or equal to the absolute value of x. So given an epsilon, choose a delta. Then if x goes from 0 to delta, we have that the absolute value of f of x will be strictly less than delta, which is equal to epsilon. Thus, the directional limit is 0. Therefore, f of x is continuous on the closed interval 0, 1. Next, we need to show that the bounded variation is the supremum and it's finite. Letting this partition from 0 to 1 over 2 have f of x naught will be anywhere I have x in the function, I replace it with 0 from the partition. That is the first item on the partition there is 0. The next one will be 1 over 2n. The next one, 1 over 2n minus 1. That is how we'll take the partition one after the other to the last one, which is 1 over 2. So when you do that properly, you're going to have your f of x naught, f of x1, f of x2, and f of x3, and so on, down to f of xn minus 3 and f of xn minus 1, and even f of xn, which is the last 0. Now, therefore, the bounded variation over f will now be the supremum of all this, where you are going to substitute all the values you have gotten from the evaluation. And when you do that properly, you're going to have summation of 1 over n, which, using the p-series test, is infinity. Hence, the series diverges and f is not a function of a bounded variation. We have another example here to prove that the function of f is continuous but not a bounded variation. Firstly, we prove that f is continuous on 0, 1. We need to show that f of x goes to f of 0, which is 0, as s goes to plus 0 for directional limit. So for x going from 0 to 1, f of x is equal to x sine pi over x. The sine function is bounded, of course, by 1, and hence the absolute value of x sine pi over x will be bounded by x. Given epsilon greater than 0, choose delta to be epsilon, then the interval x to delta will have the absolute value of f of x to be strictly less than delta equal to epsilon. This shows that the directional limit also is 0, thus f of x is continuous on the interval 0, 1. Next, we need to show that the bounded variation, which is the supremum, is finite, or that it exists. Letting this partition from 0 to 1, the bounded variation of the supremum, when you do all the necessary substitutions, this is what you're going to get. And when you continue with the simplification, you're going to factor out 4, because when you look at what we have done properly, you will see that 4 was just repeating itself at the numerator. So you factor it out so that you can have smaller digits to work with. So everything boils down to 4 summation of 1 over 2n plus 1 equal to infinity. So using our test again, any of the tests you use, whether it's ratio test, limit comparison test, Rabi's test, any of the tests you wish, use it to check whether that summation of this series converges. And we've done that and we discover it's infinity, hence the series diverges and f is not a function of bounded variation. Properties of functions of bounded variation. Number 1, the sum of two functions of bounded variation is also a bounded variation. Also, prove that the bounded variation of f plus g is less than or equal to the bounded variation of f plus the bounded variation of g. Prove. The bounded variation of f plus g is equal to the supremum of the summation of f plus g x j minus f plus g f x j minus 1. What it simply means is that anywhere I have f in the original definition, I now replace it with f plus g. And when you do that and substitute properly, you're going to have the supremum over the partition of summation of absolute value of f of x j minus f of x j minus 1 plus g of x j minus g of x j minus 1. And when you continue, that will give us the supremum of summation. Summation will go in and it will become summation of f of xj minus f of xj minus 1 plus the supremum and the summation of g of xj minus g of xj minus 1. And that will give us the bounded variation of f plus the bounded variation of g. So similarly, for the difference, bounded variation of a difference, it just follows from what we have done for the one of sum or addition. The proof of the bounded variation for f minus g less than or equal to the bounded variation for f minus the bounded variation for g is left as an easy exercise. Properties of functions of bounded variation continues. Now is another one here. If f is a function of bounded variation on AB, then it is also bounded variation on AC and CB, provided C is belongs to the closed interval AB, and conversely also. So the bounded variation of f over AB is equal to the bounded variation of f over AC plus the bounded variation of f over CB. The proof of this also is left as an easy exercise. The algebra of bounded variation. If f and g are functions of bounded variation on AB, then f plus g is also bounded variation. F minus g, they are bounded variation. Their scalar multiplication is also a bounded variation, and so on. Provided the functions are bounded variation, the addition will still be bounded variation. Their subtraction will be bounded variation. Their product, whatever, even division will also be a bounded variation. Thank you for listening.